Welcome to an Introduction to Forces Problem Solving. Yay! Muppet Flynn! So, what we're going to do in this video is go through the problem solving process for forces that's laid out in the very specific forces problem solving guide. So I recommend that you have that with you while you're watching this video, because then you'll be able to see the 13 steps as we go through them. So I'm going to do a medium, hard, easy problem. I don't know what to call it. And I'm going to go through it in all its gory detail, because I want you to see exactly how each of the steps work. When you get more comfortable with force problem solving, you'll be able to skip some of the steps, because you'll be able to just say, okay, bloop, that's that, and you won't have to think about it much at all. But for this example, I want to go through every single step, talk my way through what those steps mean. So the problem we have, a 45-kilogram child slides down a metal slide that is angled at 20 degrees from the horizontal. If the child is traveling at 1.2 meters per second, by the time she's 1.8 meters down the slide, what is the coefficient of friction of the child on the slide? Okay, a lot of numbers in there. So, first step, I have my list right here. Draw a picture. Okay, I can draw a picture. We have, let's see, can I put that there? We have a kid sliding down a slide. Whee! And the slide is at 20 degrees from horizontal, and we know the length traveled, how do we know that? 1.8 meters. And when she's 1.8 meters down, her velocity is 1.2 meters per second. We know her mass is 45 kilograms. The angle was 20. I'm actually doing number 2 right now. So I did my picture and now I'm doing number 2. I automatically jump into it. Figure out your knowns and unknowns. Well, what are we given? So I'm just reading through the problem and saying, okay, what are the numbers, and is there other information like constant speed or accelerating that we care about? So we know the final velocity is 1.2 meters per second. We know the distance traveled was 1.8 meters. I think that's it. Mass, da, 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 da. And we want to know what is the coefficient of friction. All right, so step 1, draw a picture. And again, this isn't, this is just a basic picture. Nothing high art value is necessary, which is good because I never learned to draw very well. Then your knowns, what are we given? And unknown, what's our target? So that's step 1, that's step 2. Step 3, choose the object of interest. Well, what's the object of interest in this case? The kid, so the child that is moving down the slide. So the object of interest is the child. 4, draw a force diagram for the object of interest. Okay. Now, with the force diagrams, one of the reasons I like to use boxes instead of dots or circles is because if I have something at an angle, I draw my box at an angle to remind me that, oh, this is an angled problem. All right, what forces act on the child as she's sliding down the slide? Well, the easy one, Earth is pulling down on her with a force equal to her weight, which is mass times gravity. And let's see, the slide is supporting her. That's the normal force. But remember, the normal force is always perpendicular to the surface. The surface is like this, perpendicular is like this. The normal force right here, the slide supporting her. And we know there's friction. So what direction is friction? Well, she's sliding down the slide. Friction always is opposing motion, so friction is going to be parallel to the surface, opposing the motion. All right. And what else do we have? What other objects are interacting with the child? I don't see anything else. You might want a forward force here. You probably want a forward force here. But is anything outside of her pushing her down the slope? Is there someone behind her pushing her down? No. Why does she go down? Well, what's the only thing in this direction? Gravity. Yeah, so gravity is what makes you go down a slide. You probably knew that if you hadn't thought about it in exactly that way. So here's our force diagram. We have 3 forces. Number 4, that was force diagram. 5, choose a coordinate system that aligns with the direction of the acceleration or the motion. So the direction of motion is that. That's the direction of the motion. Is there acceleration? Yes, because she's presumably speeding up as she goes down. So I'm going to say this is the direction of my acceleration, which means I'm going to do a coordinate system aligned with this. Now, I usually pick the acceleration in the x direction. It doesn't matter though, you could pick it in the y direction. So if you'd had these rotated, that's fine. All right, so that's our coordinate system 6. Figure out if forces are balanced or unbalanced in each direction. Okay, so in the x direction, in this direction, which is along the slide, are the forces balanced or unbalanced? And that means we have to think about, is it accelerating or is it not? Well, I said there was an acceleration in this direction. So we have an acceleration, which means the forces are unbalanced. All right, in the x direction, unbalanced. In the y direction, so that's perpendicular to the slide. Is there any motion in this direction? Is she flying away from the slide or slowly falling into the slide? Nope. So in the y direction, there's no motion at all. And if there's no motion, that means there's no acceleration. And if there's no acceleration, the forces are balanced. So that's the way to think through that. That is number 6. Number 7 is set up a force table for the x and the y direction forces and put all your forces into their appropriate places. Okay, so what do we have here? I need to set up a force table involving these 3 forces, breaking them up into their x and y components. So I'm going to have the 3 forces are friction, normal, and weight. And what I'm going to do is I'm going to break those up into their x components and their y components. So when I talk about a force table, this is what I'm talking about. Because, as I said when we were first introducing forces, we have to deal with forces in the 3D world. Luckily, most of the problems we deal with are 2 dimensions, so we have to think about the forces in this direction separately from the forces in this direction. They are different things. All right, so let's figure out what the forces are. Okay, so x direction, so in this direction, what do I have for the friction? And if you are having trouble figuring out, the directions, I often take a ruler or a pencil or something and I say, okay, this is the x direction. What's happening in the x direction? Well, all of the friction is in the x direction, and it happens to be in the negative x direction because I said down was positive. So all of the friction is in the x direction, there's nothing in the y direction, and it's in the negative x direction. So the friction is all in the x, in the negative x. Normal force. What do we have with the normal force? Well, that's in this direction. That aligns perfectly with the positive y direction. So I have positive normal force as a y. Is there any x component? Is there any this or this to that? Nope. None. All right. Looking good so far. And now we get to the hard one. So, what direction is the weight in? Is it in the x direction? No. Is it in the y direction? No. It's in both. So we have to break it up into its components. So we'll take this force vector and find the vector components for it. And this is something that you'll just want to write down, try to memorize something, because your life will be much, much easier if you can just remember when you're making the triangle to break up the weight, always just drop it down opposite that normal force, because if you do that, this is the same as the angle of the incline. So if I draw this a little bit bigger, we have the full mg is straight down, and then I need to break it up into a component along these 2 lines. So there's my y component, and there's my x component. And if I do that, this is the angle of the incline. So that's the 20 there. That 20 is equal to that 20, if you draw your vectors like this. And that's what I'm going to recommend you do. If you want to go through the geometry of making sure that that angle is actually that angle, it's really easy. But if you can just trust me too. I've done this once or twice. So we have this. So what is the component of the weight in the x direction? Well, the x direction here is opposite the angle. SOHCAHTOA, opposite is the sine component. So what we have here is, I don't have enough room, mg sine theta is the x component of the weight. And is that in the positive or negative direction? It's going this way, so that's the positive x direction. The y component, okay, so this piece is adjacent to the angle. That must be the cosine piece. So we have mg cosine theta. And is that positive or negative? Well, it's going down and to the right-ish, so down is opposite what I chose as positive, negative. All right, so that is what a force table is. That's how you take these vectors, and separate them out into their x and the y components, because we have to treat all the x's separately from all the y's. That is number 7. 8, use Newton's second law in each direction. All right, I need some space. I need to erase. What can I erase? Oh boy. How are we doing? All right, Newton's second law. So that is the sum of the forces in the x direction equals the mass times the acceleration in the x direction. Sum of the forces in the y direction equals mass acceleration y direction. And what we're going to do with this step here is tell us, okay, do the forces have to add up to max or do they have to add up to 0? We said in the x direction they're unbalanced, we have acceleration, so it's going to look like this. In the y direction there was no motion, no acceleration. Balanced forces mean the forces have to add up to 0. So add up all the forces in the x direction. That's what Newton's second law is saying. Add the forces in the x direction. So I'm going to take this table and just run straight down and add up all those forces. Negative friction plus mg sine theta equals mass times acceleration in the x direction. All right, same thing in the y direction. Add up all the forces in the y direction, set them equal to 0. Straight down, nothing there. Plus normal minus mg cosine theta equals 0. So this and this, these two equations are kind of the core of a force problem. Using Newton's second law to get these equations is really the key to solving anything. All right, so I dealt with that. So once we have our x and y Newton's second law taken care of, then what do we do? What's next? Use F equals mu n if necessary. Okay, if there's friction in the problem, you have a third equation available, which is the fun equation, the friction equation. And we definitely have friction involved, so there's equation number 3. That was easy. 10, use kinematics if necessary. Is there kinematics in this? Well, the forces are associated with accelerations. We weren't given an acceleration. We know that in the x direction there is acceleration, but we don't know what that number is. We need to know that number. So in this case, we do have to use kinematics. So we're going back to the first couple weeks of class where we built our chart of the 6 kinematics variables and then had those 3 equations that we used. So for this one, we got to do that. X initial, X final, V initial, V final, acceleration, time. We want to know that. What do we know? And unfortunately, I had to erase our lists of knowns and unknowns. But the change in distance was 1.8. So I can just say, I'll start my origin at the top of the slide. Down the slide, 1.8 meters. And she was traveling 1.2 meters per second at the bottom of the slide. Do we have any other information? I don't know anything about time. We're looking for acceleration. What about initial velocity? You can make a really good assumption here that she was starting at rest at the top of the slide. So I could say, I know that. All right, we don't know time. There's only one equation that we have that doesn't involve time. That is this equation, v final squared equals v initial squared plus 2 acceleration change in x. We know that. we know that, we know 2, we're looking for a, we know delta x, got it. And that's 0. So v final squared equals 2a delta x. So if I solve this for acceleration, v final squared over 2 times delta x. Is that right? Yep. V final was 1.2, so 1.2 squared over 2 times 1.8. All right, grab a calculator and find out what that acceleration is. And hopefully I have my notes here too. Oh, good, I do. Okay, so 1.2 squared over 2 times 1.8. Is that plus 0.4 or 4? That's 3.6, 1.4 to 3.6, that's 0.4. 0.4 meters per second squared. Okay. So that was number 10. Use kinematics if necessary. And I had to use it because I didn't know what my acceleration was. And my acceleration is right there. 11, plan how to get your answer. All right. So now that we know what our acceleration is, how can we get our answer? And at this point is where I usually go back to my initial chart and variables and say, what the heck are we looking for? What was the problem asking? Because you might have lost track by this point. So we were looking for the coefficient of friction. All right, so we want the coefficient of friction. We need to figure out how to get that. Well, the only equation we have is this one. So we want mu. Okay, so the only equation we can use is friction equals mu times the normal, which means we need the friction force and we need the normal force. Can we get those two? Okay, we need the friction force. Let's see about this one. We want the friction force. Let me get a different color. We want the friction force. Do we know the mass? Yes. We know gravity. We know the angle. We know the mass. And we just calculated the acceleration. Got it. Okay, so for friction, we're going to use the top equation. Minus friction plus mg sine theta equals ma. Normal force. And since the friction and the normal force are always perpendicular to each other, they can't ever be in the same chart. They can't ever be in the same equation. So I'm going to look in the other direction. Yeah, and I'm going to use n minus mg cosine theta equals 0. Because, let's see, I'm looking for n. I know mass, I know gravity, I know my angle. Ha! We know everything. We can solve it. So that's what I mean by planning a solution. Just say, what do I have to start with that has my unknown variable? And then, okay, what do I need to solve these two? What do I need to solve that? What do I need to solve that? Sometimes the step can go down a ways. In some of the harder force problems, it will go down a long ways. But in this case, it doesn't look too bad. So, once we have planned our solution, number 12, solve for your unknown. Actually do it. Okay, I'm going to rewrite this to give me normal equals something. That one's easy because you just drop that over there. I got to rewrite this to get me friction equals something. Bleh. If that goes over there, I'd have a positive friction. This stays here, mg sine theta, and this goes over to the other side, so minus ma. Is that right? If I switch all the signs, positive f minus minus. Yeah, that's right. All right, so I have friction, an equation for friction. I have an equation for the normal force. I'm going to pop them right into the fun equation. So F equals mu times the normal. Pop, pop. All right, friction equals mg sine theta minus ma. That whole piece is friction. Equals mu times the normal force, which is mg cosine theta. All right. And now, at this point, if I planned everything right and did it all right, I should have everything I need to solve for that, the coefficient of friction. So, do I know my mass? I know mass, gravity, I know the angle, I know mass, I know acceleration, mass, gravity, angle. Got it. Got it. At this point, we can toss our numbers in there. So, let's see what were our numbers. And actually, before we toss numbers in, I want you to look at this equation. I always like to stop and say, can I make my life easier at all? Is anything zero? You know, I do that with kinematics. Can I make my life easier at all with this? And I can. Do you see something in here that I can get rid of? There are 1, 2, 3 terms. Is there anything that is in all 3 terms? Yep. There's a mass. Now you can't get rid of mg because this is ma. So mg you can't get rid of, but you can get rid of m. There's an m in all 3 terms. So I'm going to do that. I'm going to get rid of the masses. Ta-da! I just made my life easier. So my equation ends up being g sine theta minus a equals mu g cosine theta. All right. And we can rewrite that. At this point, if you want to put the numbers in, you know, go ahead and put the numbers in, or you can rewrite it for mu equals and do it that way, however you're comfortable, whatever way you're comfortable. I'm going to rewrite it for mu. Mu equals, okay, so to get mu alone on one side, I need to get rid of the g cosine theta. So divide both sides by g cosine theta. So I have g sine theta minus a over g cosine theta. Ta-da! All right, what do we get? 9.8. Now we're on to step 13. No, 12. We're still on 12. Sine 20 minus the acceleration, which was 0.4, over g cosine 20. All right. Grab your calculator. Give it a try. Let me see what I got. 0.32 is what I got. I got 0.32. Okay. We just did 12. Don't stop there. Don't stop there. 13. Solve and check for reasonableness. Check your answer for reasonableness and units. So, we don't have a unit here, but that's okay, because this doesn't have a unit. Mu is just a number, 0.32. Let's see, it's usually between 0 and 1, so that is reasonable. 0.1 is really icy. 0.8 is really hard to push, so don't take the icy end. Makes more sense for a slide. You don't want a lot of friction on a slide. So I would say this is reasonable. We have answered the question. It's reasonable. It doesn't need a unit, so that our unit is correct. And I think that's all we have. The only other thing that people often mistake is when we use G, we just want 9.8. We don't use negative 9.8, because if you go back and look at our force diagram and our Newton's second law equations, we had weight pointing down, and that's where that negative sign is. So don't use a negative 9.8 for G. It's just the number 9.8, because we already took into account that it's downward. So don't double count that negative. That's one of the things to remember. G is just the number. Other than that, I think we've answered everything in glorious, gory detail. And if you have any questions, always just let me know. I'm happy to work with you on whatever you need. Good job for following.